And we welcome our next speaker here. Our next speaker is Mathieu Munsch. He received engineering degrees and a PhD in Grenoble. In 2017, he created the company Qnami, of which he is also the CEO. Him and the company are actively involved in the European Quantum Flagship Program, and he's today going to talk more about quantum metrology here, in particular a new quantum microscope that he's going to present here. So welcome to our Quantum Summit, welcome to stage Bob, Mathieu, and we're looking forward to your talk.
Thank you very much. Thank you for this invitation, for the opportunity to present. I trust that you can see my screen now.
Yes, we can see it.
Great. So yes, I want to talk today about Qnami, our startup, and how we think that our technology, our quantum sensing and quantum metrology technology can help support the development and actually enable the development of new computing technologies. We are a startup founded a few years ago, located in Switzerland, about 15 people with a wide range of expertise on quantum, going from the quantum materials to the quantum software through the engineering, really the whole breadth of technologies that you need to spin a full product in the market. And our goal is to provide unique solutions to industries undergoing really rapid changes. And I'm going to focus today on one example, which is around computing and this state of affair that the current paradigms around computing are slowly reaching their limits. We're exchanging data at a rate that has never been met before. It's estimated that by 2030, about a fifth of the world's electricity consumption will be related to communication and computing technologies. This is the equivalent of 1,000 nuclear power plants working 24/7 just for that purpose. And while this is certainly bringing huge value to our society in many aspects, from personal consumer benefits to healthcare, etc., it is also clear that it's taking a toll on the environment. And really, there is today in this industry a big question and a big challenge around combining both the high level of performance that we need today with a much lower footprint for every device and the new technologies. The good news is that solutions exist, and I want to point out two of them, which are particularly promising. The first one is called spintronics. It uses the magnetic properties of electrons, and probably the best example is a new memory called MRAM. This has been pushed by the major foundry and semiconductor players now, and is entering slowly the market. It has great performance and a much reduced energy consumption. Another example, which I probably don't need to highlight to the audience today, is quantum computing. I think we all know now that there is a huge promise to be able to perform extremely complex calculations and solving really complicated problems for a fraction of the energy bill. Now, what's needed to take this technology from lab to really an industry grade are a few elements, and one of them is quality control tools that help steer the final developments of the product and eventually also control their manufacturing so that the yields and the reproducibility can increase. So this is what we do. We commercialize and develop solutions based on quantum sensors, allowing to diagnose these new types of technology beyond CMOS. And one of the unique value proposition that we can bring is this extremely high precision in measuring magnetic fields, currents, electric fields, or even temperature. The principle is that we use a tiny sensor that we scan over a chip of interest so that we can measure those properties and bring up relevant information to our customers. The goal then is to enable our customer to reduce the error rates for their chips. This is the critical component when you want to move from a confidential technology to a mass market application. We will, with the technology, support partners in obtaining reproducible audit trail when they develop a new technology. We allow them to remove trial and error. For now, it's mostly we build a complete chip and we test it. There's not much in between to test the quality along the process, along the fabrication. So this leads to a lot of wasted time. And eventually, we anticipate that such technology could be used in manufacturing processes to control the quality at different points in the manufacturing. The key elements is quantum sensors. And here I'd like to just mention here that we, in this world of quantum sensor, leverage what is typically understood as a weakness of quantum system, which is their extremely strong interaction with the environment. So if you build a quantum computer, you will do everything to kind of shield the environment, shield your system from the environment so that it can remain in this quantum state and you can perform these quantum math and operations. With the sensor, as long as you can control the system decently, this interaction with the environment becomes a huge asset and offers unique performance. So this is exactly what the key concept is behind quantum metrology, the use of these quantum sensors. And as a platform, we have chosen Diamond, so-called NV centers in Diamond. Those are atomic defects. They provide this ultimate resolution because the sensor is just an atomic, an atom size site. It turns out to be a system where you can locate the sensor is a small spin. It's a so-called spin, a small magnet, which we can use then to sense magnetic fields. And the other important property is that when you go from one quantum sensor to the next, they really behave the same. They rely on fundamental physical constants so that each sensor will give you the same output for the same inputs. This is critical when you want to build a sensor technology that brings accuracy and reliability. So to give a picture of this, of the type of sensor that we built, this is what we call a quantilever. So it's a particular shape that allows us to bring this atomic defect very close to the chip of interest. It's a chip which is all made of diamond and where we have created one single atomic defect in a very precise location, allowing us to do the type of measurements we offer to our customers. So really a unique technology. And the last part, which is really great about diamonds, is that it's a scalable platform, really important for us in this context and also beyond, as was explained by Sadek just before. We are using synthetic diamond, not natural diamond. This is a technology which is already available. And we are using recipes that we borrow from the silicon industry, lithography, dry etching techniques, so that we can reach some scalable production. And you can see on the right here a collection of sensors that will be integrated in the microscopes that I've shown before. So when we think of a solution, this scalability is super important, and there are a number of other ones. I'm not going to go into all details, but certainly when moving from a proof of concept a technology to an instrument that is used by real users, the need to have a specification book driven by the customer is a key ingredient. So we had to do a lot in developing a solution that is compatible with user needs, and our partnership with Oriba, a well-established manufacturing company of scientific equipment, was critical in this regard. And the other component is to have something intuitive. We want our users to be able to benefit from the quantum boost in performance, but not having to deal with the complexity that the technology brings. So it should be really hidden for the user. So this is what we achieve with our LabQ software, which is really now an interface that allows users without any technical quantum background to use our microscopes. It's also an open source platform because our users now are also academics. They explore, they push the technology, and they feed back with really useful information, sometimes even contribute to ideas that we implement later in our instruments. This slide is really important. It really shows, and this is worth highlighting today, that quantum technologies is not just tomorrow. It's not just a nice promise for the future. It does exist today. We've launched our products a little more than a year ago, and we already have four high-profile users that benefit from quantum technologies for their application, which has nothing to do with quantum technologies. We're proud to have a Nobel Prize winner, Albert Ferd, the founder of the field of spintronics that I was mentioning before, as one of our early adopters, as well as the Fraunhofer Institute, which kind of show that the industry has also an eye on that type of technology, looking to understand how this can benefit them. Flashing here a couple of applications that we have demonstrated in the past month. It really goes from giving information around certain types of memory all the way down to quite complex scientific questions on 2D materials. It's a vast range of materials that we can look into, and a vast range of devices that we can provide critical information that really help tailor their developments. We bring certain quantities that can later be used in simulations to evaluate, for example, retention rates in memories, etc. And now connecting to my introduction, we are now looking to expand the capabilities of this Proteus Q instrument, and specifically build a cryogenic version so that we are as close as possible to the operating environment for quantum computers, for example. And we can really perform a service that is as close as possible to the operation conditions for this industry. This is how you are the more relevant for the end customer. And similarly, we're looking to another system for the semiconductor industry, which would allow to accommodate much larger sample, which this industry is used to using. So stay tuned. There will be quite some exciting news around the end of the year and along next year. But also, if you are working in these industries and want to explore what this means for you and how this can benefit your own application, I'll be really more than happy to engage and discuss what we are developing and take the feedback that you can give us. So this will be my final slide. I'd like to highlight that we are still growing at fast speed, just closing a round of financing recently, and lots of open positions. So if you are looking for a position to make a short-term impact with quantum technologies, I'll be more than happy to engage and explain who we're looking for and what we're building here. And with this, I would like to thank you again for your attention and the organizers for the kind invitation. Thank you.
Thank you too. Thank you for being with us. Mathieu, first you confirmed our previous speaker's statement that diamonds are sensor designer's best friend, I would say. So it already pays off to have learned this sentence now.
Yes, absolutely. Yes, they are. And one of the reasons is exactly what I mentioned, this ability to recycle fabrication technologies or methods that are existing is one of these key aspects. When you want to design new chips, you can rely on recipes that were built for the silicon industry. Of course, you have to adapt everything, but you know what road to follow.
And you showed us some beautiful results. I think it's really some great work that you have accomplished there already. We've got a number of questions and comments. There's 2 comments in the discussion regarding your statement on the energy footprint. So the first one is the energy footprint really that much lower despite, for example, the cooling apparatus needed for superconducting circuits? And in the same direction, the second one, I thought that quantum computers will still have to be driven and read out by classical computers. What about their footprint?
Yeah, no, this is absolutely true, and will probably not risk myself into a full analysis of the energy footprint. This would be dangerous for me. But what I can say is that yes, quantum computers are not going to replace classical computers entirely. They might be driven, and they have their own problems in cooling. Still, we need to do certain problems that we need to solve and that we want to solve. And I believe that society will just move towards solving these problems, require more computational power. If you do want to do that with existing technology, you just need to scale up. And here we understand very well what it means. It's not working. It's not sustainable. So I think the only option we have is to study alternatives and make sure that they will really reduce the energy footprint, taking into account these additional factors that come in, as the comment rightfully say.
Thank you for commenting on that. There's one direct question also regarding the measurements that you've shown with the device. So how long does a measurement actually take? Like one measurement?
So this depends a bit on what you want to do, but typically you have measurements between a few minutes to 10 minutes when you want to have a first analysis and useful information about your sample. And when you're interested into really specific, detailed, high resolution, it can take up to an hour. This fits well with our scientific user base, and we're working it to make it faster when it becomes important, in particular for the industry where the speed and the throughput will need to be much faster, but the operations will also be much more focused.
Okay, thank you very much. And just like the others, of course, you will also be available for the next 15 minutes in the speaker's corner. So anyone interested in further questions here or discussions, please feel free to join Mathieu in the Meet the Speakers section, which the link has been posted to already. Thank you very much for being with us here again, and good luck to you and your company with the further developments in this. I think it's we all realize what an interesting and dynamic field this is and has become by now. So I think there's a lot to be seen here in the next years. Thank you very much, and goodbye.
Thank you very much.